Anybody have any homework questions? Okay. Well, let me go through one more circular motion example, and then we'll go into relative motion. Um, so this is an example that shows how circular motion comes into the motion of rigid bodies. So let's say that there's a hinge attached to the ceiling. And then like a rod that's rotating in that hinge. And let's say that the length of this rod is 0.5 meters. And let's say that we know there's an angular velocity of positive 10 radians per second and an angular acceleration of positive 20 radians per second at this instant. Squared, yes, thank you. And we want to figure out, if we call this point P, we want to figure out the velocity vector and the acceleration vector of that point P. Okay, well, we know from the signs of the angular velocity and angular acceleration that it's moving counterclockwise. Okay, its acceleration is counterclockwise, which means it's speeding up in a counterclockwise rotation. And if you think about the motion that point P is going through, so if I okay, so okay, so this point P is going through a circular path around that hinge. Okay, any point that you followed around of that rigid body would be following a circular path around that center. Okay, the hinge is the center of the circular motion. We know that the angular velocity is this way, and the angular acceleration is also that way. And so we know that the velocity vector has to be like this. Since the angular acceleration is also counterclockwise, we know that the tangential acceleration also has to be that way. The centripetal acceleration is always the same. It's always straight toward the center. And so now we know all the directions. All we have to do is figure out the magnitudes and combine those for vector components. Anybody have any questions yet about this? Okay, so the velocity, well, the magnitude of the velocity, the speed, is the absolute value of, it was 10 radians per second, so absolute value of 10 times the radius of that circle. If this rod has a length of 0.5 meters, can you see that that would be the radius of that circle? And so that speed is 5 meters per second. And so now we know that the velocity is in this direction at 5 meters per second. So what would that be in vector components, the velocity?
5, 0.
Yeah, it's in the positive x direction. So the velocity vector is 5, 0. And now for the acceleration, we have to do the two different parts separately. The magnitude of the tangential acceleration is the absolute value of the angular acceleration times the radius. And so that's 10 meters per second squared. That's in the same direction as the velocity. So the tangential acceleration vector is 10, 0. The centripetal acceleration magnitude is, well, you can always do it two different ways. You can do it as the speed squared times the radius, or no, the speed squared divided by the radius, or omega squared times the radius. Either one of these two. And so that is 20 squared times 0.5. Is that, no, I used the wrong one. It's the angular velocity is 10 radians per second. So square that, multiply by the radius. And so you get 50 meters per second squared. The centripetal acceleration is in the positive y direction. So as a vector, the centripetal acceleration is 0, positive 50. And then the last step is the total acceleration is the sum of the tangential and the centripetal. So that's 10 for x, 50 for y. Any questions about that? So we'll come back to some circular motion problems after we do relative motion. This is still part of two-dimensional kinematics of particles. So this is relative motion in 2D. And I realized that on the last quiz, there was a question about two-dimensional relative motion. We hadn't gotten to it yet, so sorry about that. I'll cancel that on the, but the relative motion equations in 2D are what you would expect them to be if you're familiar with one-dimensional relative motion. And so now position, velocity, and acceleration are all vectors. And you can make sense out of the relative motion equations if you think of it this way. So imagine two coordinate systems, A and B, with the same axis orientation. So the coordinate system orientations are the same. Each of these is tracking an object that I'll call O. Well, with one-dimensional motion, we were talking about two choices of the zero position, okay? And they had to be along the line because all the motion is along a line. But now what we're talking about is one coordinate system here that we'll call A, and that's the axis orientation. And another coordinate system here with the same axis, you know, the axes are in the same direction, and we'll call this one B. And both of them are measuring the motion of this object O. Okay. Let's think about the position vector as measured by each of these two coordinate systems. The position vector is always a vector from the origin to the object. So the position vector measured by A is this. So you can think of this as the position vector of O relative to A. And the position vector of O according to B is this. And notice that if you use A to measure the location not just of that object, but also the location of coordinate system B, you can think of this as the position of B relative to A, the position of B measured by A. And then what you see there is that according to the rules of vector addition, the position of the object relative to A is equal to the position of the object relative to B plus the position of B relative to A. Okay? All I'm doing is writing out the vector addition equation that you can see is clearly true from that picture. Okay, are you with me on that? And what we have is this is the same position relative motion equation from 1D, but now with vectors, you know, now in 2D. And notice that the fraction multiplication memory device still works. The, you know, O over A is equal to O over B times B over A. So that's still a way to remember to get the order right. And now if these coordinate systems and the object are all moving, you can take the time derivatives of both sides of the equation. So ddt of both sides and it gives you the velocity and acceleration relative motion equations that we had in 1D. Just now everything is vectors. So everything works out the way that you would guess it would work if you had to guess. So velocity of the object relative to A is equal to the velocity of the object relative to B plus the velocity of B relative to A. And same with acceleration. If you take another time derivative, so the acceleration of O relative to A is equal to the acceleration of O relative to B plus the acceleration of B relative to A. And if it ever comes in handy, we also have these relationships for vectors. The position of, A relative to B is negative of the position vector of B relative to A. Same with velocity, same with acceleration. So if you need to switch those subscripts in order to make sense out of your problem, you can switch the subscripts, just multiply by a -1. So now velocity and acceleration. Okay. So this all works. I mean, you don't really have to remember a new approach or anything. We're just talking about things in terms of vectors now. All the rules with the subscripts that you did in 1D work in 2D. So let's see this work in 2 dimensions. So let's say that you're in a car. Let's make it a convertible so you can see what's going on. And you hit the brakes or run into something. And drop your coffee. Okay, let's see. Yeah, that's good enough. Okay, it's like a low rider. And meanwhile, while all this is going on, your kid in the back is filming it with your iPhone. Okay, so this is the coordinate system. The coordinate system is fixed to the car, moving with the car. The car's velocity is this way. If you slam on the brakes, What's the direction of the acceleration? Opposite. Okay, so let's say that the acceleration magnitude is, let's say 30 meters per second squared. That's pretty big, but let's say that's what it is. According to the camera, what's the acceleration of the coffee? Okay, so let's set this up as, so C is the coffee, G is the ground, not the coffee grounds, and I call it V for vehicle. But all these things are moving together. So V is the vehicle, the passenger, the camera. Okay. And we're talking about acceleration, so we want the acceleration equation. So the acceleration of the coffee relative to the ground is equal to the acceleration of the coffee relative to the vehicle plus the acceleration of the vehicle relative to the ground. And now we can start to fill in what we know. This coffee, once you let go of it, is in free fall. So if our coordinate system orientation has the y-axis up, then the acceleration of the coffee relative to the ground is 0, negative 9.81. Okay. Do we know the acceleration of the coffee relative to the vehicle? No, that's what we're trying to find, right? We're trying to find this camera that's mounted to the vehicle. What does it see for an acceleration? So if it measured a bunch of positions through that camera and then figured out a function and took time derivatives, we're figuring out the acceleration that it would think this coffee cup had. Okay, this is what we're looking for. Do we know the acceleration of the vehicle relative to the ground? Yeah, we're given that it has a magnitude of 30 meters per second squared. We know it's in the negative x direction. So this is negative 30, 0. And so now just solve for this variable. The acceleration of c relative to v is equal to add negative 30, 0 to both sides, subtract negative 30, 0 to both sides. It's like adding 30, 0. And you get 30, negative 9.81 meters per second squared. Okay, so that's why if you're driving in your car and you have something sitting on the console or whatever, and you slam on the brakes, to you sitting in the car, it looks like that thing flies forward, and it runs into the dashboard. That's not really what's happening to an observer that sees it happen from the side. If your car was glass and they could watch this happen, they would just see this thing once it happening to an observer that's on the ground. But to an observer in the car, and also that observer on the ground on the street watching it would see the car accelerate the other direction. It would be like the, okay, so let me draw this. So here's the coffee cup. And to an observer on the street who's watching this coffee cup, it would look like this coffee cup's going however fast, 30 miles per hour, horizontally. And then it becomes a projectile, and from that point on, it follows a parabolic motion like that, according to the rules of free fall. Okay, it wouldn't fall straight down in their view. It would be a projectile that started out at 30 miles per hour, but its acceleration would be straight down. And what that person would see is that the car would have a negative acceleration that pulled it out of this path. So the car would still be going forward, but it would be going forward more slowly than this as it came to stop. Okay. So to an observer on the street, the coffee is just in projectile motion. To a person sitting in the car, that's not what it looks like. If you actually measured everything out carefully, it wouldn't look to the driver like that coffee cup was in projectile motion. It would look to the driver like that coffee cup accelerated forward into the dashboard. Okay. Any questions about that? Okay, so now I want to talk about rolling without slipping, and we'll use circular motion and relative motion in this. So this is the last topic in 2D particle kinematics. Rolling without slipping. And this uses circular motion and relative motion. Okay, so if you choose a coordinate system with the y-axis pointing directly out of the surface, so for example, if the thing's rolling along a horizontal surface, the y-axis is like this. That means the x-axis is like this. And if the surface is that, then we're going to use a coordinate system with the y-axis this way and the x-axis this way. And if it's like that, then the y-axis is going to be this way and the x-axis is this way. Okay. And this is the center of the wheel or the ball or whatever is rolling. Then the velocity of the center of the thing that's rolling is going to be negative omega times the radius of the thing that's rolling for the x component and 0 for y. And the acceleration of the center is going to be negative alpha r and then 0 for y. So any rolling without slipping problem, you're going to use these equations. And those are derivable using the relative motion equations. I'm not going to go into the derivation, but I'm going to show how to use it with relative motion. Question? Okay. All right, so let's say that, let's say this is horizontal. And you have this wheel rolling with an angular velocity this way of, let's say, 2 radians per second. And let's say it's speeding up with an angular acceleration of 10 radians per second squared. We know it's speeding up because those are the same direction. And the radius of this wheel is 0.5 meter. The center, let's call that C. The point at the bottom, let's call that B for bottom. And then at the top, T. Let's figure out first what's the velocity and acceleration of C. Then let's figure out the velocity and acceleration of the top. And then the velocity and acceleration of the bottom. Okay. So the first part of this is just using the using the rolling without slipping equations to calculate the velocity and acceleration of the center. So the velocity vector of that point C is just going to be, in our coordinate system, is going to have the y-axis straight out of the surface, x-axis horizontal, okay? Because that's the coordinate system we're always going to use for this. Okay, so the velocity of c is negative omega r, and then 0 for y. What's omega in this example? Yep, positive 2, because it's counterclockwise. So this is positive 2. We have the negative sign in front of it, times the radius, which is 0.5. And so we get a vector of negative 1, 0. This is a velocity. This is meters per second. Or you could think of this as the velocity is in this direction with a magnitude of 1 meter per second. So if this is rolling, does it make sense that the velocity would be in the negative x direction if it's rolling counterclockwise? Just intuitively. That has to be the relationship unless there's sliding at that bottom point. We're not considering that. So that direction makes sense, right? What direction would you expect the center of this wheel to be accelerating? It's also going to be in the negative x direction because we know that it's speeding up. Okay, we know that the rolling is speeding up because the two angular quantities are in the same direction. Okay, so that means that the translational acceleration of the center also has to be in the same direction as the velocity vector. So the acceleration of the center is negative alpha r 0. So that's negative of, we have positive 10 for the angular acceleration. Times 0.5, that's the radius, and 0. So we get an acceleration of the center of the wheel of negative 5, 0. And this is meters per second squared. And so you could also think of this as a vector in this direction with a magnitude of 5 meters per second squared. So if this was the wheel of a bike or a car or something, this is how fast the actual vehicle is going, the cab, you know, or the seat or whatever, because all that is rigidly connected to the center of the wheels. Okay. All right, so now let's think about how to calculate the velocity and acceleration of the top. Okay. Well, what we want is the velocity and acceleration of the top relative to the ground. Okay. If a problem doesn't specify what something's relative to, it always means relative to the ground. So how can we do this with the things that we know how to solve? Well, the velocity of the top relative to the ground, we can think of using the relative motion equations as the velocity of the top relative to the center plus the velocity of the center relative to the ground. This one is what we just calculated. This one comes from the rolling without slipping equations. this one, so now imagine that you had a camera, a coordinate system that was fixed, that was moving along with the center of the wheel. What would it see the other points on the wheel doing? It would just see those points moving around it in circular motion. Do you see that? Okay. It wouldn't know that it's moving. It would just see the points going around it. And so this is just circular motion. Okay. So now we have a part that comes from rolling without slipping. We actually already did that in part A, so we don't have to do that again. We can just bring in the values we got. And we have a circular motion part. And then we just add those two parts together and it'll tell us the velocity and acceleration of the top. Anyone have any idea, any thought on, so think about first the velocity of the top. Anyone have any idea what the velocity of the top of a wheel is doing compared to what the center is doing? It's moving at 2 times, so the speed of this is twice this. Okay, that's what we're going to see. And actually, if you take a picture of a bicycle wheel using a slow enough exposure, you have to get the exposure like exactly right to show this. But what you'll see is that the spokes up at the top are really blurry, and the center is relatively crisp. Everything, as you get closer to the top, is moving faster and faster until it's going twice as fast as the vehicle itself. Okay, so let's see how that works. So this we got in part A. We're just going to add that on at the end. So what we have to do is the circular motion. So we want the velocity of the top relative to the center. And to do that, we're going to think of a circular motion where this thing is moving with, what did I say, the angular velocity is 2. So there's an angular velocity of 2 radians per second and an angular acceleration of 10 radians per second squared. And we want to figure out what's going on at the top. We know that the radius is 0.5 meters. Okay, what do we know about the directions of these vectors? So we're treating it like the center is still now. What's the direction of the velocity vector of that point at the top? It's to the left. It has to be tangent to that circular path. Okay, so there's the direction of the velocity vector. I think I'll just leave it like that for now, but normally we draw the velocity vector, then we draw the tangential acceleration, centripetal. I'll do those when we get to acceleration. Okay, so the magnitude of the velocity, the speed, we're going to use the circular motion equation that says we take the absolute value of the angular velocity and multiply it by the radius. And so that's 2 times 0.5. So 1 meter per second. We know that velocity is in the negative x direction. And so the velocity of t relative to the center is -1, 0. Okay. And now put it together, the relative motion equation says the velocity of t relative to the ground is equal to the velocity of t relative to the center plus the velocity of the center relative to the ground. That's -1, 0 from the circular motion, plus the velocity of the center relative to the ground that we got in part A, and so you get a velocity vector of -2, 0. So the top point is always moving twice as fast as the center. In rolling without slipping. Any questions about that? Okay, so we sort of covered a lot of ground today. We started with that circular motion example, but then we talked about relative motion, and then we used relative motion in the first part of rolling without slipping. You got the new rolling without slipping equations. I'll finish this example tomorrow. To be continued. Okay, that's all for today.